Okay, let's talk about projectile motion. Projectile motion is often considered by IB and A-level students as one of the hardest topics in physics, in part because there are so many different questions that can be asked about the trajectory of the projectile. Questions like, what is the maximum height reached by the projectile? What's its final velocity? Or how long is the projectile traveling for? And how far does the projectile actually travel before impact? All of these actions are happening at the same time and can easily overwhelm us in knowing how to even start answering one of these questions, let alone go about finding any of these variables. So, let's fix that. We're going to look at something I like to call the 10 commandments of projectile motion, a set of 10 rules and concepts that, if followed when encountering these kinds of kinematics questions, will act as a cheat sheet to help us start our calculations correctly and carry us on through to our final answers. So, let's get started. Commandment 1. We have to treat the x and y motions of our flying projectile as completely separate and independent to one another. Basically, the parabolic trajectory that a projectile follows looks like one fluid motion to our eyes, but actually consists of two separate motions that happen simultaneously. Firstly, the flying projectile is moving up and then down, its y motion, which carries it up to a maximum height just before gravity wins in pulling the projectile back down to Earth. At the same time, the projectile is also moving forward horizontally, its x motion, which allows it to travel some distance away from its launch point. So, in order to get through projectile motion's questions, it's super important that we treat our calculations for the y and x dimensions of the trajectory completely separately. Where exactly are both of these simultaneous x and y motions coming from? Well, if we take a closer look at the velocity vector of the projectile at any point in its motion, we'll see that at all times of flight, its velocity has a horizontal x motion component and a vertical y motion component. If we were to plot these two components against a grid, we'd see that the horizontal component is always parallel to the x-axis and is therefore the portion of the velocity responsible for pushing our projectile forward and away from its launch site. We'd also see that the vertical component is always parallel to the y-axis and is therefore responsible for our up and down motion. This vertical component is particularly useful and interesting to us because it's the portion of the velocity that will be competing with gravity, but more on that later. Commandment 2. Whenever we get given a projectile motions question, even before looking at any of the answers our examiners would want us to find, we should always begin by resolving this initial velocity vector into these two components and give each component vector its specific magnitude, so we know which numbers to use when we're calculating the x motion and the y motion. A generic start to a projectile motions question might say something like, a stone is thrown from a cliff at 30 degrees to the horizontal, with an initial velocity of 20 meters per second. But what we're going to do immediately is figure out how much of this 20 meters per second are going into pushing the stone forward horizontally, our x component, and how much are going into lifting the stone upwards against gravity, our y component. Now, since we have to treat the x and y motions completely separately, that means we better only use our horizontal velocity component for any x motion calculations, and our vertical velocity component for any y motion calculations. That'll make sure that we're isolating each motion in our calculations and give us the best chance of finding the answers that are relevant to each dimension. Commandment 4. Now, although the x and y motions are completely separate, and we need to treat them in our calculations as such, they are linked by one thing and one thing only: time. Think of time as the glue that links together our two motions. So we can use time as a way of shifting our segregated calculations from the x world of things into the y world of things, or the other way around. And by the way, the examiners use this exact idea to make the projectile motions questions feel harder than they actually are. So, it benefits us to think of time as a literal bridge to move between x motion and y motion calculations. Here's exactly why the projectile motions questions feel so tricky. Let's do some exam analysis. In any question, you'll be given what I call raw ingredients. Basically, your starting values and numbers that you're expected to use to make your way through the question. In projectile motion, these raw ingredients are usually things like your initial velocity and its angle to the horizontal, and the initial height from which the projectile is being launched. Now, the majority of students expect to just be able to take these raw ingredients, squeeze them into Suvat equations, and have them neatly pump out the final answer the question is asking for. The problem is that examiners have made sure that these raw ingredients are not enough to jump straight to the final answer they're wanting you to find. So, students that go about trying to answer projectile motions questions this way will usually encounter some missing piece of information, which ends up discouraging and blocking them in the journey through the question. Now, we fix this by realizing as exam takers that the questions we're presented with are rigged by examiners who purposefully want us to take our raw ingredients and find what this missing piece of information is first, before then combining everything into calculating our final answer. And more often than not, this missing piece of information is some value of time. Now, this can seem a little strange when you first start doing it, because it can feel like you're making calculations that are heading towards a completely different direction than the one you're trying to take. But this two-step process is one of the key ideas behind unlocking projectile motions questions and making them feel much more manageable and predictable. So, at this stage, it's useful to start understanding what raw ingredients we're generally going to need to use to answer the 4 main projectile motions questions we mentioned before, and which of these questions belong more to the Y motion and which belong more to the X motion. Commandment 5. The time a projectile spends in the air is solely dependent on its Y motion. So, when it comes to finding any values of time, we're going to focus exclusively on all the Y motion components for our calculations. Things like the vertical component of our initial velocity and the initial height above the ground the projectile might have been launched from. So why is it that the time a projectile spends in the air depends only on its Y motion? Well, it's because the Y motion is the one under permanent influence from gravity. Think about it. The vertical component of the projectile's initial velocity runs along the same axis as the vector for the acceleration due to gravity, the y-axis. This means that this component and gravity are constantly competing with one another, and gravity is constantly influencing the projectile's vertical velocity and thus its vertical motion. And the projectile can only keep moving through the air if it still has some altitude. Look at it this way. If you were taking off on a plane and the engine suddenly burnt out, how long would you have before things go bad? Well, that would depend on how high above the ground you are, right? And also how quickly the plane was gaining altitude before the engine shut down. Right after this moment, the plane would still be able to gain a little bit more height because it had some initial vertical velocity, but the second the engine stopped pushing the plane up against gravity, gravity will start eating away at that initial velocity until it eventually becomes zero. Now, once that happens, gravity gets the upper hand and starts sucking the vertical velocity down into a negative direction, accelerating the plane downwards. So, how long your plane stays in flight has nothing to do with how fast it might be moving forward or horizontally. You only have as much time as you do initial height and initial vertical velocity before gravity will do its thing. So time is solely influenced by the Y motion. Let's break up the projectile's entire parabolic trajectory into 2 main chapters. In Chapter 1, the stone gets launched and flies until it reaches its maximum height. In Chapter 2, the stone starts from its maximum height and begins accelerating down towards the sea. Gravity is now making the vertical velocity turn negative and increasing its magnitude in the downward direction until it has no more height left to fly and its motion is stopped. So, if we wanted to find the total time the stone spends traveling through the air, we just need to figure out how long Chapter 1 takes, then how long Chapter 2 takes, and add those 2 numbers together. Let's take a closer look at Chapter 1. During this phase, the vertical component of the initial velocity allows the stone to gain some height. But, as with our plane, this vertical velocity is pointing opposite to the acceleration due to gravity, meaning that its magnitude starts shrinking immediately after launch until it hits zero. The stone will only be able to gain height for a small amount of time, which we'll calculate shortly. For now, the key idea here is that the maximum height reached by the stone is the moment in its trajectory when its vertical velocity is zero. So, when you read maximum height in a question, your mind should jump straight to thinking vertical velocity becomes zero. I can use that with Suvat to find the time taken for the stone to hit its peak altitude and then find what that altitude is. Using only our vertical vector components to keep our y motion completely separate from our x motion, we can use the suvat v equals u plus at, where vy is our final vertical velocity for chapter 1, so 0 meters per second, uy is our initial vertical velocity, u sine theta, a is our acceleration due to gravity, and t is time. If we rearrange this equation, we can solve for t and find how long it takes our stone to reach a final vertical velocity of 0, its maximum height. So, if our stone was launched at an angle of 35 degrees at an initial velocity of 20 meters per second, then our vertical initial velocity is 20 sine 35, approximately 11.5 meters per second. Plugging everything into our rearranged suvat, we then find that it takes the stone roughly 1.17 seconds to reach its maximum height after being launched. So now let's move on to chapter 2. Here, when it comes to the vertical motion, this basically becomes a freefall situation. The stone is starting off with an initial vertical velocity of 0, since it's starting from its maximum height. And gravity is going to accelerate this velocity vector, essentially increasing its magnitude over time, in the downward direction, which makes the stone fall back down to Earth. Let's say the stone reached a total maximum height of 50 meters above the ground. We can then use the suvat 1/2 of at squared plus ut and rearrange to solve for time to find how long it will take the stone to fall this distance. Now, conveniently for us, since the stone starts from maximum height, its initial vertical velocity at the start of chapter 2 is 0, which allows us to cancel out the ut term from the suvat equation. So, rearranging for time and plugging in our values, we obtain an answer of around about 3.19 seconds. When it comes to total time spent in the air, we just add up the two values we found for the two phases of time and see that this stone travels for a total time of 4.36 seconds. This is all the time the stone has to travel as far forward as it possibly can, but that's going to be an x motion calculation, and we'll talk about that later.